Okay. Hello, everyone. I hope you can hear me. And welcome to the sdRan version 1.1 Techinar. We have 3 speakers today. So let me give you a quick introduction to us. First, we'll have Joe Thome, who is Vice President of Business Operations and Marketing at AirHop Communications. His responsibilities include managing programs and relationships with operators, ecosystem partners, and key industry consortia, including ONF and TIP. So hi, Joe. We'll also have Corey Maudlin, who's a wireless systems and software engineer at Facebook. He spent many years on wired and wireless communication systems, and for the last year and a half, he's been working on Open RAN, developing software and contributing to ORAN standards related to the near real-time RIC. So thanks for joining, Corey. And myself, I am Saurav Das. I'm VP of Engineering at ONF, responsible for the engineering deliverables in several projects. In the past, I have worked on delivering data center fabrics, which runs in production at Comcast, and virtualized broadband fiber to the home networks that runs in production at Deutsche Telekom and Turk Telekom. I spend most of my time these days with our topic today, which is sdRan. So, just if you have not attended our previous Techinar, which was for the 1.0 release, let me catch you up. So sdRan as a project, we should really think about it as a solution, right? So yes, the near real-time RAN intelligent controller is a key component of the sdRan solution, but almost as importantly, we intend to have both XApps, and this is all using ORAN terminology. We intend to have XApps that we ourselves write, but also encourage other third-party vendors and contributors to contribute their XApps, and to make it easy for people to write applications that are relevant in the RAN. We provide a software development kit so that you need to know very little about the internals of the RIC platform, but still be able to write XApps. So we will talk a lot more about the SDKs that the platform offers. But that's only half of the story, because at the same time, we need to work with commercial disaggregated RAN vendors, CUs, DUs vendors, and of course that has to work with the corresponding radio units and a mobile core. So we take care of ensuring that our RIC platform, as well as the apps, integrate with disaggregated RAN solutions from multiple vendors, and we look at this end-to-end, right? That as a solution, it should work end-to-end. It's all about interoperability, and the engineering processes about QA and tooling and producing releases, and eventually doing certification. It's part of our goals, right? But to help in this process, what we also do is that sometimes it may not be possible that we are introducing a new feature, and the vendors have supported that feature in their CU/DU. So what we also have is that ONF builds its own white box CU/DU solution on hardware, right? So white box, and we implement the new features to serve as a reference platform with which different vendors can get an idea about how to implement that features in their software and hardware. To test the solution at scale and also be able to do demonstrations which require, in the RAN space, a lot of these things have to do with multiple pieces of equipment, an entire RAN, many base stations, many cells. And that's sometimes hard to do if you just focus on hardware. So what we have also built is a RAN simulator, and you will see a demonstration of that today. But it allows us to create, dozens or even hundreds of cells and many thousands of user elements, handsets. And then we can showcase our features on this RAN. So this is all that goes into the sdRan solution. And of course, we need to work with, we can work with different mobile cores or radio units. We also intend to work with other people who are interested in creating the SMO that works with our near real-time RIC. Okay, so a little bit also, I'd like to talk about the different organizations in this space. There is, of course, ONF and our sdRan project. But of course, there is the ORAN Alliance that formalizes the specifications, the interfaces for disaggregated RANs. So we work with our partners very closely, and this is what you're going to see in the 1.1 release. We work very closely with our partners to develop these solutions, these use cases, but also we have created a joint task group by which ourselves, our partners, we work together and provide input to the various organizations, right? ORAN or ORAN's software wing, which is the OSC that you see over here. But we provide input on use cases, on implementation details that contribute back to ORAN, that ORAN formalizes into standards, and then we consume them and OSC consumes them, and so on. Very recently, we've also started this work with ORAN OSC to develop, because OSC also has their own RIC platform. And so we are working with them to try and develop this SDK, a portability SDK, as we call it, so that X apps can be written in a way that can be ported across different RIC platforms. And you'll hear more about that in Corey's talk. And of course, lastly, telecom infra project TIP, we have a lot of synergy with them in terms of the goals that they have of introducing new use cases and being able to show them in deployments and trials. And again, Corey will talk more about our work with TIP. But actually, we can see this working in this 1.1 release that I'm going to talk about, where in fact, one of the specifications that ORAN published, we tried to implement that, found an issue with it, fed it back to ORAN, and they changed the specification to overcome the issue that we had identified. And similarly, when we were implementing it, we had a lot of questions. We had a lot of doubts about the specification, and we reached out to ORAN, and they helped us to understand. Actually, the initial implementation that we had done was just plain wrong, and ORAN helped us understand where we were going wrong, and then we fixed it and we patched our release. So this is a perfect example of how we are helping ORAN, and they're in return helping us out. This is exactly what the industry needs. So having said all of that, I do want to give you a very quick introduction of what we had in the first release of sdRan that we did back in December of last year, and then that can set the stage for understanding what has gone into the most recent release. This is version 1.1 that we did at the end of Q1 this year. So in sdRan 1.0, as I said, ONF builds reference hardware, right? So we have a reference white box that works on Intel servers and uses software-defined a radio box from National Instruments. And then with antennas over the air, we can talk to either phones, handsets, or UE software that can be put in a similar white box combination of a server and a software-defined radio box. So over the air, we can have phones or this UE software that comes from the OAI project, Open Air Interface project, to work with our LTE CU-DU that also comes from OAI project, but we have enhanced it to create this E2 interface by which it can speak the ORAN standard interfaces to our what we call the µONOS RAN intelligent controller, or the µONOS-RIC. So this enhancement of the OAI software running on the white box hardware today, well, not today, in the version 1.0 release, supported the ORAN standard E2 application protocol version 1.0. And that uses ASN1 encoding, also coming from ORAN, the ASN1 definitions. And of course, it uses SCTP for transport. And in this first release, we supported one of the service models. And in the ORAN world, everything is defined on the basis of service models. And this particular service model is for key performance metrics that can be exported from the RAN hardware. And we've supported 1.0 version of the KPM service model. So inside our RIC, we of course have this piece over here which we call E2 termination. It's meant to terminate the the E2 application protocol and talk to the CU node and eventually the DU node. But it does more than that. It actually, while the external communication is using ASN1 encoding, internally within the RIC, we use gRPC and protobufs. So what that means is that E2T has to have an understanding of not just the E2 application protocol, but also the different service models that we support in a particular release. So these service models we build plugins for our service models that the E2T can then consume and then go through this process of taking the information coming from the RAN nodes and converting them into a format where the rest of the RIC understands and operates, right? So I won't go into details of the internals of the RIC, but I do want to point out that in the first release, we had the beginnings of a software development kit that was written, that is language specific and was written in Go language. And then using that SDK, we had an application, a KPI monitoring application that would subscribe for this particular service model and then ingest the data that is coming via this service model from the RAN nodes. So all of this runs, this is the setup on hardware. Of course, this is all of our software in the RIC is containerized, runs on a Kubernetes cluster, gets managed using Helm charts. And so this stuff is, of course, outside the box, but this is, while this is running on hardware and works with our 4G mobile core, that is, we call it OMEC. As part of the 1.0 release, we also had an ability, if you don't have the hardware, you can run it completely in a VM or in a server, and we call that sdRan-in-a-Box. So you can take all of the containerized software, which is already containerized in terms of the RIC, but also the software, the CU, DU, and user element software, as well as the mobile core. Notice that there is no RU, there's no over-the-air transmission over here, but you could run the containerized versions of all of this software together with the RIC and see how this is all working. It's really useful for development and test to run it in sdRan-in-a-Box. We also, in this first release, had the beginnings of our RAN simulator. So the RAN simulator, we had an older version of it that we were converting to use ORAN specific interfaces, E2AP and the KPM service model. But it was really the beginnings of it. A lot of things were still hard-coded, but the framework was being developed to build RAN simulator. But in this release, the version 1.1 release, we actually worked a lot on RAN simulator, and you will see that. So in version 1.1, I'll give you a very quick overview of all the things that went in. First of all, as we were developing 1.1 release, ORAN was releasing new versions of the interfaces that they were working on. So we had to upgrade from E2AP 1.0 to E2AP 1.01. Okay, and that means upgrading our CU E2 agent software. It means upgrading our RAN simulator as well as our RIC to speak that particular version of E2AP. Similarly, there was also the KPM spec that we supported in 1.0. ORAN released a new version. Well, at the time of the release, they had not finalized the KPM 2.0. There were pre-release versions 2.1, 2.2, 2.0.3. So at the time of the release, we settled on KPM 2.0.3 service model. And again, that meant upgrading our CU, our RAN simulator, and as well as the service model plugins that are consumed by the RIC, as well as the application via the SDK to use KPM 2.0, which is not backward compatible. Actually, it's a big change from KPM 1.0, but that is the way forward. And so we upgraded our stack to use that. One very interesting thing that came into this particular release is that we want to enable XApp developers to write their applications in the software that they are most comfortable with, or they want to write it. And so we always had the Golang SDK, but in this particular release, we have a contribution from Facebook for an SDK for Python, for apps written in Python. And that's really advantageous because, one of the goals is to use machine learning and the AI to do more things more intelligently in the RAN. And a lot of the frameworks for AI ML are actually written in Python. So to have a Python-based SDK so you can write an application that leverages those frameworks is really, really useful. I'm very happy with the contribution that has come in for this second SDK that works with our RIC. And then we actually use that. This is the collaborative work that we have done between AirHop, Facebook, and Python to develop this SON application, self-organizing network application, to run on top of the RIC with AirHop's eSON server. That's a commercial product that's actually not part of the release. You'll need a commercial agreement to work with AirHop but that commercial product actually works with an app that leverages the Python SDK to work with our RIC and create the solution that you will see today. So we also have, as part of the release, something that mimics the AirHop eSON server. Now, it won't actually do the functions that the eSON server does, but at least you can test this particular interface between the app and AirHop's product using this particular test server. Now, we want to keep these SDKs in sync. So otherwise, the whole purpose is lost for multiple SDKs being supported by the platform. And so we developed an example XApp that also does the same thing, and we call this Pci Conflict Resolution. And we'll talk a lot more about that in today's talk. But we developed this X application to use the Golang SDK to do the same thing that this combination does over here, but maybe with just about, it's an example, a reference XApp. So maybe does maybe 10% of the functionality, but it will resolve simple conflicts that are being reported from the RAN. And it helps to keep this particular things in sync. So obviously, again, I said in the ORAN world, everything is done with respect to service models. So for this particular use case, this PCI conflict resolution use case, we worked together to develop this service model that we call RC-Pre. And so again, that had to be implemented in the RAN simulator, as well as a service model plugin for the RIC and the SDK to understand, so you can you can understand what's coming from the RAN and then be able to take action to resolve conflicts in cells. So that service model development was part, of course, of this work. As I've mentioned before, we worked a lot on the RAN simulator. You will hear a little bit more about that in this talk, to be able to create the RAN, expose the service models related to the PCI use case, and become part of this demonstration, because you need multiple cells to do that. It gets a lot harder to do that with hardware. We also built some tools that can feed into RAN simulator. You can generate a topology, a RAN topology of cell towers and how many cells on the tower, and what's the distance between the towers, what angles are the cells facing, and so on. So that's all part of the topology generator. And then you have the ability to create conflicts, right, using a PCI generator. So you can create the conflicts and then have this stack resolve the conflicts automatically. And you will see that as part of the demo as well. Of course, there is a GUI that shows you the state of the RAN as according to the RAN simulator. So that's part of the release as well. And finally, while we are working on use case, we are also still working on the infrastructure that supports it. So as I mentioned, our RIC is all, it's microservices based, it's containerized, it's run in a Kubernetes cluster and managed, installed using Helm charts. And the nice thing about Kubernetes is that there is an API that they expose for their inbuilt resources. And by resources, I mean things like Kubernetes understands like pods or deployments or services. And it also gives you the ability to create custom resources. Okay, so using this operator construct, so you can create custom resources and custom logic, so that the RIC APIs, some of them get exposed as Kubernetes APIs. Okay, by extending the Kubernetes APIs, so you can use something like Helm to work with those APIs. And there are certain advantages for operating this system using this construct, as opposed to installing things and then doing post-install jobs through other pods and so on. So it's an improvement of the infrastructure that's also part of the 1.1 release. But today, having given you this overview of all the changes that went into the version 1.1 release, for the rest of the talk, we want to focus on what was a big part of the release, which was this joint collaboration between AirHop, ONF, and Facebook to develop this PCI conflict resolution SON use case on top of our RIC. So at this point, I'm going to hand over to Joe Thome, who will walk you through AirHop's collaboration with us. So Joe.
Yep, thank you, Saurav. Great introduction. I kind of paint the picture of what we were doing. So yeah, we AirHop, really was looking to join ONF and begin collaborating within the community with the express purpose of trying to accelerate the sdRan near real-time RIC capabilities by leveraging our commercially proven, commercially hardened ESON platform and applications, by onboarding those as XApps, helping drive these service model definitions, as Saurav indicated, and really take the overall ecosystem that is required in order to pull a complete open RAN, ORAN architecture platform together make it mature and something that operators want to drive into their networks as soon as possible. So in order to do that, we needed to start somewhere. So we have our ESON platform, which is, again, commercially deployed through Open RAN disaggregated platforms today. The ESON system has essentially the ability to take near real-time information from the cells that it is managing, and then within the platform itself, it's able to then essentially not only automate and optimize different applications for a particular cell, but also dynamically coordinate information across different cells. So within the system, we have this microservice that we call the Cell Optimization Engine, or COE, and that microservice has that responsibility of taking the specific application for automation and optimization for each cell, and then doing that dynamic coordination. So at the end, you end up with a network level optimization decision, and then the ability within the ESON system to push those parameter changes or RAN constraints back into the RAN, all within near real time as defined by ORAN. So this is where we are, and the objective is to take this commercially hardened platform and move it into the ORAN architecture, leveraging the collaboration through the ONF community. So this is the goal, taking this architecture on the left, which is what we have in production today for 4G, 5G systems. The real-time connection between the RAN and the ESON system is through, today, a proprietary API. And we have a client sitting into the RAN, which can be deployed as either a binary client or a gRPC protobuf definition. So both are supported fully. And the goal is to then obviously migrate those capabilities and those applications as XApps onto the near real-time RIC, and interfacing with the near real-time RIC APIs that are, again, exposing the services that are available on that near real-time RIC. Well, the key one obviously being E2 interface, providing, again, the similar real-time parameters from the radio access network to take these network level decisions. So this was the goal, to push this type of acceleration. So how did we do it, and what was our focus? So in general, we were looking to leverage, obviously, our current existing ESON platforms. So really no change, looking at taking a deployment of our ESON system, again, in a Kubernetes deployment, either in a public cloud system like AWS EKS, or into an ONF Ether deployment. And be able to get access to the ONF RIC services, and this was done through this. Sorry. And this was done through the XApp adapter application. That we worked in collaboration with Facebook. And then, of course, those services are exposing the E2 AP and the E2 information coming up. So the goal through this collaboration is to expose the commercially deployed services and applications that we have, with initial focus on PCI optimization, which can be done in real time. It can be done in a maintenance window, very flexible in terms of the capabilities and configurations that the operator wants to deploy it. Deploying near real-time radio access channel optimization parameters, near real-time mobility load balancing, MRO, as well as near real-time uplink and downlink intercell interference coordination, and other applications into our roadmap as well. So this initial collaboration was specifically focused on 4G PCI to be used as somewhat of a pipe cleaner application. Let's take something that's fairly well contained, well defined, uncover what are the changes in the service model that need to be deployed, and build the capabilities of this XApp adapter in order to implement that. So this is what the focus has been. So in terms of the parameters that we required for this, or we pulled in, was obviously the cell information parameters, the ECGI, the frequency, the PCI pools, the neighbor relation table, and then the ability for that nRT, that neighbor relations, to be removed or to expand. Based on neighbor discovery. And then, of course, the system itself, identifying whether or not there are any collision or confusion events, detecting those, and resolving them, and pushing the PCI changes back into the RAN platform through the XApp adapter, as well, and then down into to the E2 to the RAN elements itself. So this is really the scope of the current demo that you'll see today. But we're continuing to drive efforts. So what's next in our in what we're doing? So we're actively migrating this capability beyond 4G into a 5G PC optimization, and extending the next key feature, the dynamic mobility load balancing for both 4G and 5G. So we're going through the same process today, where we essentially have a service model up here through the ESON API, driving these XApp adapter capabilities to expose the services to the ONF near real-time RIC, and then that in kind is pushing the service model influences down here into the E2. So whether or not there's a need for a new service model or an enhancement to existing service model. So these are the aspects that we're continuing to push. And with that, thank you for the opportunity to share this, and we look forward to helping drive the acceleration of the sdRan near real-time RIC.
All right. Thanks, Joe. I think I won't wait for Saurav.
Okay.
I'll jump in here and try to share my screen. Great. Yes. So thank you, Saurav and ONF, for this opportunity to speak. As Joe and Saurav have both mentioned, we've had an excellent collaboration working with them on this use case and others in the future. So I'm going to spend this time to talk about the SDK that both Joe and Saurav talked about. So just to start, as Saurav mentioned, my name is Corey. I am a wireless systems and software engineer at Facebook. And people often ask us at Facebook, why is Facebook invested in connectivity? Why are we doing this? The reason is that we believe that fast, reliable, and accessible connectivity is good for people and businesses of all kinds, including ours. Our goal is to bring more people online to a faster internet, and supporting Open RAN and RAN intelligence is one way to do that. This integration among ONF, AirHop, and Facebook shows how we can bring a production XApp to the market using open standard interfaces with minimal complexity and engineering effort. So we support and contribute to ORAN, as Saurav was talking about. ORAN publishes specifications and supports open source software. As most of you are aware, ORAN is defining standard interfaces like the E2 interface between the RAN and the RAN Intelligent Controller, or RIC. ORAN is also in the process of defining standard APIs between third-party apps and the RIC. Together with our partners at ONF, AirHop, and others, we are actively contributing to the API's definition in ORAN. This enables app vendors like AirHop to deploy their SON products across RAN vendors. Oops. Saurav also mentioned about TIP. We also support and contribute to the TIP RAN Intelligence and Automation, or RIA subgroup. The Telecom Infra project and the RIA subgroup in particular, it plays an active role in bringing together alliances like this one among AirHop, ONF, and Facebook. The PCI use case, like 11 others, has been identified and contributed to RIA by operators and vendors. RIA works with MNOs and vendors to bring these use cases to trials and to the market. RIA members represent 39 operators and 90 vendors in the RAN controller space. So at Facebook, our primary role in this demo with AirHop, ONF, and Facebook was in providing the software development kit, or SDK, and a service that uses the SDK to interface with the AirHop app. The SDK is a key part of a strategy to avoid market fragmentation and enable a broad ecosystem of innovative app solutions. We plan to make the SDK open and freely available and to base it on ORAN-defined APIs. This has benefits for everyone, for app vendors to reach a larger market, for OEMs to draw on a large family of apps, and for operators who will see performance improvements on their networks across OEMs. The goals of the SDK are straightforward: to make it simple for app providers to develop and test their apps, and to enable portability across RIC platforms. Our vision is that multiple RIC vendors agree on an ORAN-defined standard interface. The SDK exposes simple APIs and abstracts the vendor-specific architecture of the RIC platform through that interface. This way, an app from one vendor can interoperate with RIC platforms from any other vendor. Going one level deeper, the SDK can be thought of as two components: a RIC platform independent layer and a RIC platform specific layer that we call the portability layer. The portability layer terminates and abstracts whatever protocols and service splits that are implemented by the RIC vendor. For example, if we look at the ONF RIC, the portability layer terminates the gRPC protocol that Saurav talked about, used by ONF. The platform independent layer defines standard APIs, encodes and decodes standard service models, and provides other SDK functionality that's not necessarily specific to the RIC. The idea is similar to apps that run on your phone. Like if you look at Android, for example, one app using standard APIs can run on devices from multiple manufacturers. So this way, from the point of view of app developers, the APIs remain the same across platforms. Each platform provides its own implementation to expose standard APIs. As we see here, the ONF platform uses protobuf over gRPC, but the ORAN software community, or OSC, RIC design directly passes ASN1 over TCP. This portability layer terminates these protocols and data formats. So what's in the SDK? The SDK provides more than the ORAN APIs. It includes libraries to access popular databases and a REST interface, for example. It includes a test and logging framework, code examples, and tools like Helm charts and RIC stubs to ease the deployment and development. With the SDK, you can run an example out of the box in any Kubernetes environment. We used this same SDK approach in other programs internally at Facebook. Internally, of course, portability wasn't the goal. It was ease of use and uniform application of libraries and Python async as an example. Those were the main goals. With multiple apps running from multiple, even internal developers, we found that the platform is more robust and easier to manage if everyone is using the same SDK, which enforces good coding practice and uniform management, control, and visibility into the apps. Okay, so this slide has a lot going on, but this is a Techinar. So here we're showing a more detailed diagram of the architecture used in this PCI demo. If we start at the bottom, ONF provides a RAN simulator that Saurav talked about that not too surprisingly is called the RAN sim. And it talks to the RIC through a standard ORAN E2 ASN1 over SCTP interface. On the northbound side of the RIC platform, the services in the ONF-RIC run gRPC servers. The SDK terminates the gRPC connections and exposes simple APIs to the AirHop client that is in the adapter. The AirHop client in this example talks to the AirHop ESON system shown at the very top here. Also over another gRPC interface with ESON running in the cloud. This architecture allowed fast development without significant changes to the production ESON app. And finally, to show an example, the APIs are defined, as I said, from ORAN defined messages. Here we can see an example API that could be used to subscribe to a set of RAN parameters, such as a stream of the number of connected users, or PRBs, physical resource blocks. The trigger and actions that you can see in the API, they describe a specific set of parameters, like the number of connected users, if you look at that example. Trigger and actions are keywords. They're defined as part of the ORAN E2 access protocol. The definition of the trigger and actions, it depends on what you're subscribing to. ORAN is also defining standard service models, what they call service models, that I think of as the APIs to define the triggers and actions and other aspects. The triggers and actions can also be pre-standard or proprietary, as we did in the PCI demo, because the standard service models are still being defined in ORAN. So as Joe and Saurav both said, we are working with AirHop and ONF on other use cases using the same approach. And we look forward to the continued collaboration. And thank you again.
Okay, thank you very much, Joe and Corey. So one thing I would like to point out also as part of this work was our work with RAN simulator, and I'm hopefully you can see that part of the screen. Give me 1 second to share. Okay, hopefully you can see that now. In the RAN simulator, which we have really worked a lot on in this particular release, we have the idea is to support the ORAN interfaces and expose characteristics of the RAN to the RIC using these E2 interface, right? That is standardized by ORAN. So essentially, we have the concept of an E2 node, and that E2 node is expected to be the CU today, or even a monolithic G node B or E node B. But in a disaggregated RAN, it is expected to be the CU today, and eventually it could also be the DU. But that CU-DU combination then has, actual associated cells. So we have models for what is the E2 node that talks to the RIC via an E2 agent and exposes, the attached cells. We also have models for user elements that are assigned to the cell. And while not in this release, but in work that we are doing right now to simulate handover use cases, the UEs can also be put on a path, a route, and you can do calculations that the UE reports as measurement reports based on the received signal reference power that it sees from its serving cell or neighboring cells, and so on. The cells can also have neighbor relations. So the UEs report to the serving cell all the neighboring cells that it also sees. So you can have established relationships between a cell and its neighbor relation table, which is something that we used in this PCI use case, and have all of that be exposed towards the RIC. Now, one thing is very important to point out is that this is a simulation of this SDN interface. The goal in RAN simulator is not to simulate the 3GPP control plane. So, in the real world, user elements are talking to the CU, using an RRC protocol. You won't find the RRC protocol being simulated in RAN simulator. Similarly, there is a whole process called automatic neighbor recognition or resolution, ANR, where the CU and UE are exchanging messages to understand and resolve between the PCI values that user element reports and what is the ECGI or the cell global ID for that particular cell. None of that negotiation is actually happening inside RAN simulator, but it's really the outcome of that negotiation that gets reported up to the RIC. That is the part that RAN simulator takes care of. And it does so by establishing a generic set of what we call metrics that can be assigned to these entities, the main modeled entities, such as cells and nodes and user elements. So this is how we establish the PCI that is assigned to a particular cell, or the neighbor relation tables that are getting reported for that cell, and that then makes its way up to the RIC. So what the RAN simulator then looks like is, yes, we have these simulated entities, the E2 nodes and the cells behind them, and objects that represent the user elements, and of course the E2 agent that actually talks to the RIC. Actually, E2T is part of the RIC, and so this arrow should really be down here. But the important part to understand over here is that you could preload through a YAML file an entire RAN topology and assign the metrics to that RAN topology that then get reported as part of the models to the RIC. And you can bring in all these service models that are ORAN defined or defined pre-standard by us, such as the KPM service model or the RC-Pre service model that we developed for this particular use case. And those then also get represented in the data that we are reporting to the RIC, and the actions that the RIC and the XApps take on those models in the RAN simulator, and the metrics that are, or the attributes that the model supports. We have also built in gRPC APIs so that you can make changes at runtime to the simulation. So in this particular work that we are highlighting, this Pci Conflict Resolution, you can always load a RAN topology with the attributes associated to the models, such as the PCIs, where you have created conflicts to start with, right? But also at runtime, you can create new conflicts or new confusions, and that's also, you know, a PCI terminology. You can create conflicts and confusion at runtime, and then see again it getting resolved through the RIC and the XApp. Similarly, you can take down E2 nodes or take down cells and simulate failure scenarios using these runtime gRPC APIs. And using those APIs, we can expose state that the RAN, or rather the RAN simulator, sees in a graphical user interface, or on a CLI as well. And you can export things to, you know, external time series databases. So hopefully this gives you a pretty good idea about all parts of the stack, starting from what Joe was talking about, the ESON server and the SDK and RIC that Corey was talking about, all the way down to the RAN simulator. So it's really a perfect time to give you a very short demo. I have a link here on YouTube, which is a slightly longer demo. A slightly shorter version of that is what I'm going to show you as part of this Techinar. So here we go.
AirHop, Facebook, and ONF have joined forces to demonstrate a production XApp running on the ONF-RIC platform using the Facebook SDK, all using ORAN-defined standard and pre-standard interfaces.
We have the ONF-RIC platform in the middle here, and we have a RAN sim speaks E2 to the RIC. We have the SDK, we have the XApp, and we have the AirHop ESON. So let me zoom in a bit and show you a bit of what's inside, what they do. So the RIC has a bunch of components, but today I'm going to highlight mostly the E2 subscription service and the termination service. So the E2T is what talks to the E2 nodes. So the RAN sim is the component that kind of emulates it for now. And the E2 node has a few cells associated with it. The app, when you see FB-AH-XApp, that's the app. I'll be pointing that out a few times. So this is where the logic happens for passing the information through between the RIC and the ESON service. So the ESON service is running in the cloud in AWS for today. The rest of it is running locally on my laptop in the Helm environment. Yep. So this is the AirHop ESON UI. We have, I have 5 nodes in this, 5 cells in this, but the ones we worried about right now are the first 3. We have these 3 ECGI with 3 PCI, and we have, this is the RAN sim state. So we have this map in here to help illustrate. We have these 3 nodes, 1, 2, and 3, and they are, these 2 are connected. We have this neighbor list here. And so these are the 3 we're talking about with the neighbor relationships. And so what I'll do right now is I will change the PCI and you can see it change. So right now I'm going to change this third node, 75, and then I'm going to change it to one that doesn't conflict, and you can observe the messages going through. So this, I'm going to change this guy. It'll go from 3 to 5, and you'll see the same thing here. The logs here I'm showing is that this is a RAN simulator. This is the E2T, and these are the log messages from the XApp. So I have the headers here. So the app, it says I found the updated PCI to 5, and you'll see here, this changes to 5, and this changes to 5 as well. Sounds good. Okay. So what I'll do now is I'm going to change it, like I can change it to 6, and it'll change to 6. Here and here. And so let me explain the lines here. So green means they're neighbor relationships, but there's no conflict. But what I'm going to do now is I'm going to add a conflict. So I'm going to change this guy from, so since these are neighbors, I'll make it a conflict. So I'll change this to 2. And what you'll see here is, okay, so I'm going to change this to 2. And then hopefully this line will be clear. So it's got changed to 2. The line changes to red, marking a conflict. I'll get, this is where it changes to 2. This is the change request from ESON to 124. And this also then flips green, showing that it changed to 124.
Okay, let's see. So hopefully that gave you a really good idea about the work we have done jointly. And just to give you a taste of what is coming next, this was not a one-time thing, okay? We continue to work with each other, and I think our collaboration will continue to grow this year with more people getting involved. They're already getting involved. And so, you know, some of the things we just have to do, right? You know, keeping up with the ORAN standards, you know, new versions of the interface, new service models that are coming. Some of the things that we are all are doing right now, for example, the PCI use case was done on, you know, using a service model based on 4G. And we are now making changes to that to be 5G. And, you know, similar changes, either upgrades or, you know, moving towards 5G will happen, you know, all over the stack. New use case, of course, keep coming, right? And so that sometimes, that always means, you know, sometimes we have to develop new service models that have not yet been standardized. So 2 that we are working on right now, one with AirHop and Facebook is on mobility load balancing, and you will hear about that in the coming months. Another one is a mobile handover that we're again working with Facebook and Intel Labs. And that's also very exciting work, and some of the things that I was talking about in RAN simulator point towards that with the UEs moving. And of course, we continue to do integration with more and more, not just XApp developers using our SDKs, but also commercial RAN vendors. So right now we are pursuing integration with Radis's CUDU software. And sdRan, it's important to understand, is a standalone project, but it's also a key component of ONF's Ether project. And if you haven't heard of that, I strongly encourage you to go and take a look at Ether, which is ONF's private 5G solution for enterprises, private 5G and edge cloud solution for enterprises. So do take a look at the Ether project. So we're at the top of the hour, and we've done a fairly good job of answering most of the questions that have been come online. So we'll take a couple of minutes to highlight a couple of the questions. Several of you have asked that when is sdRan going to be open sourced for everyone? That's a very good question. Right now, it is accessible only to ONF members, and we expect that sometime this year we will be making it available to non-ONF members, everyone essentially. Some other questions that we haven't answered. There's a question about this. Is there scope for the use of multiple RICs with the ransom in the future? So as I said, the RAN simulator simulates this E2 interface. Right? It does not simulate the 3GPP protocols or the data plane bearer state that 3GPP defines, but it does hold true to the standardized E2 interface coming from ORAN, as well as the standardized service models and some pre-standard service models that we are defining. So in principle, it can be used with any other RIC platform as well. So I hope that answered the question. Corey or Joe, is there any other question that you'd like to highlight? The ones that we have already answered?
Yeah, I think there's a question about, I guess, faster timescale applications. Certainly, we have some specifically around interference management and interference mitigation that is in the roadmap for us pulling in as a next app and integrating into this. So look for that coming down the road.
Okay. Corey, anything on your part?
Yeah, there was a question about whether this SDK is the same SDK being discussed in ORAN. So what I would say to that is yes and no. So as I pointed out, the SDK, as we think about it, is many things, including the APIs, but also libraries, database access, things like that. So in terms of APIs, yes, that is, we are discussing that in Working Group 3. All of us here on the call and others are actively contributing to that discussion in ORAN.
Okay. So I believe, I think we have answered all of the questions that were asked. If there's nothing else that we'd like to highlight, we thank everyone for their participation in this Techinar, and hopefully you will hear from us very soon about the continuing work that we are doing collaboratively and bringing in other ONF members and partners into the sdRan solution. Thank you all, and have a great evening or day or wherever you are joining us from the world. Thank you. Bye.